次，我们非常荣幸邀请到演讲嘉宾 Flex CTO Paul Diemer 先生。Paul Diemer 先生将为我们带来题为加速 AI 数据中心规模化之战的精彩分享。For our next session, it is our great honor to welcome our speaker, Mr. Paul Diemer, CTO, Embedded and Critical Power at Flex. Mr. Paul Diemer will share his insights titled The Race to Scale AI Data Centers. Ladies and gentlemen, please welcome Mr. Paul Diemer.
Good afternoon, everybody. Thank you for the kind introductions. As mentioned, I'm Paul Diemer. I'm the CTO at Flex, where I focus on embedded and critical power infrastructure for the data center. I'm excited to be here at Computex for the first time. I have to admit, as somebody from the northern part of the United States, I was not ready for the heat and humidity that we found here in Taiwan. So I appreciate the strong air conditioning here that we have at Computex. My job is essentially to figure out what is the physical infrastructure needs for the next generation AI data centers. And that covers everything coming from the power off the grid down to the silicon that's consuming that power. But before I begin, I need to take care of a quick announcement. I'd like to acknowledge that Flex has recently announced its intention to spin off its cloud and power infrastructure business into a standalone independent public company. Now, pending the completion of that transaction, the portfolio that I'm going to discuss today is expected to be part of that new company. Now, we're excited about the opportunities that are going to come with that, but we're going to remain focused on delivering for our customers, throughout the transaction process. Now, what we're seeing in the industry today isn't just growth, though there's plenty of growth for sure. It's a shift in how data centers are built. AI isn't just increasing the demand, it's changing the constraints in how we define the overall system. And the key that I want to focus in on for today's discussion is that we're moving away from data centers being designed as individual components, and we're moving towards develop them as complete systems that can be designed, developed, integrated, and deployed all together. So let me start by addressing the data behind the demand curve, because the numbers are quite extraordinary, right? And they directly shape every engineering and supply chain decision that we're making in the industry today. If you look back at the historical data from IEA and the Goldman Sachs projections for the future, you can see that we started in 2010 around 200 terawatt hours for data center consumption. And over the next 10 years, up to 2020, that grew to about 240 terawatt hours. So about a 25% increase over 10 years, fairly moderate growth. But then things changed. When we look into 2025, that spikes to 600 terawatt hours. And again, huge growth out to 2030, where we're going to exceed 1,000 terawatt hours. So nearly doubling in just 5 years. But I think the real interesting thing is the composition of that curve, right? It's the AI portion of it is really driving the demand. It's increasing from 90 terawatt hours in 2025 up to over 400 terawatt hours in 2030. So that's a 4 to 5 times increase in power just for the AI portion of data centers. And it's not just the power that's increasing. It's also the amount of CapEx that we're investing in this industry. We've heard the numbers thrown around quite a bit, so it's probably not shocking at all anymore to hear that $1 trillion is going to be the annual spend that goes into AI part of data centers by the 2029 timeframe. So there isn't a single number here that's meant to really jump out. It's really the magnitude and the speed of the growth that's really the impressive part here. Okay, first, I'd like to share a brief word on Flex, where they sit in the ecosystem, because that's going to kind of shed light on what our perspective is for the rest of the presentation. Flex is a global manufacturing company. We have about 140,000 employees, 27 billion in revenue across 30 different countries globally. Our data center business covers everything from the power infrastructure, liquid cooling systems, the racks and enclosures, and also the IT hardware integration. Now, we're obviously not a hyperscaler. We're not a chip manufacturer. We're the company that those people rely on to build the physical infrastructure for the data centers in the future. And that includes everything from the medium voltage switchgear down to the cold plates at the GPU die. And that position really gives us a unique vantage point in the industry. We see the silicon roadmaps coming from the customers before they're released. We see the product roadmaps from the hyperscalers, from the co-locations, from the sovereign AI guys. We're seeing those all simultaneously at the same time. And we're in the middle of building, certifying, and delivering those systems at the scale that we saw on the previous slide. So what I'm going to share today comes from that operational reality of executing to meet these demands. And we'll talk about what I think is hard about meeting that scale, what I think is breaking almost in the industry right now, and how we need to adjust in order to be successful and hit the targets that we have ahead of ourselves. So first, I'd like to introduce a framework that I think helps clarify why this is a harder problem than it necessarily looks like on the outside. I think there's 3 different axes of scaling that are happening all at the same time. And they're not just independent axes, they interact with one another. The first axis is the scaling up. And this is the one I think that we talk the most about, and it's probably the most well known. This is the shift in the compute density and the power being consumed. Right, 3 years ago, a typical AI rack was around 10 to 20 kilowatts per rack. Today's NVL72 is around 150 to 200 kilowatts. And the next generation of platforms are targeting around a megawatt per rack. So that's a 50 times increase in just 5 years. And every one of those watts, it has to be delivered efficiently, but then also effectively removed as heat through the system later. The second axis that we're talking about is the scaling out. This is the interconnect challenge. How racks within a facility communicate and how you design for coherent, low latency compute clusters at scale. And as the rack power increases, we also need to adjust the power conversion architecture, the busway design, and also the cooling loop. All that has to be re-architected to around the compute structure, not the other way around. And the third axis that we're going to talk about is the one I think is least discussed, but it's probably where we're going to have the most operational headaches. And that's the replicating of that infrastructure across dozens or hundreds of sites globally. And we're going to do that at build rates that used to be years, and we're going to condense that down to months. And the internal data that we have right now shows that in the next 5 years, so from 2025, say to 2030, there's obviously an increase that we're seeing in the power density, the site energy use, but there's also an increase in the unique part numbers and SKUs that our suppliers are using. So that all points to the increased complexity as we try to scale out across the globe. So it's not just one hard thing that we're addressing, it's 3 hard things happening all at once. So before I get into the things I think are actually challenging, it's going to slow us down, I'd like to acknowledge the most common ones, the challenges that are most often discussed, because they're also quite important for us. The first is power availability, right? Grid capacity is definitely a challenge for us. Some programs are now moving towards on-site generation, and we expect that small nuclear reactors are going to be in use by 2030. We also have to deal with the supply chain, the fragility of the supply chain, right? We know that the supply chains that are engaged today, they're still quite fragile, right? They haven't really moved past that point. And we're seeing from a sustainability standpoint, as we move towards 1,000 terawatt hours, we're garnering a lot of attention from the regulatory committees and also the public, for good reason. We also see supply chain disruptions. The lead times on our high power components, those things remain extended to the point where they're impacting program schedules. So these are all of the known knowns. These are the things that the industry is currently working on today. And so I'll spend the rest of my time talking about what I'm going to call the hidden challenges that I think are actually the real ones that we need to work on to be successful. So the first of my hidden risks is the shifting market landscapes, right? We're seeing a total redesign, re-architecture of what makes a data center for AI. We're moving from 48 volt racks to 400 volt and then 800 volt DC, and we're already talking about 1500 volt DC. And these are driven by the physics, right? We're not doing it just for fun. At 150 kilowatts per rack, the higher current becomes impractical at the lower voltages. So we use higher voltages to reduce the current, reduce the amount of copper used, and it allows us to shift the power conversion outside of the IT rack, freeing up additional space. And we know that as the industry is shifting towards 1 megawatt racks, the use of this higher voltage DC is going to become a necessity for AI at scale. And the cooling architecture is shifting along with this. Air cooling works up to about 50, maybe 100 kilowatts per rack. But beyond that, the airflow and the energy requirements become quite impractical, which is why liquid cooling is really mandatory for AI compute. And the thermal system has to go along with it. The OCP guidance for CDUs to support an AI rack just 2 years ago was around 1 liter per minute per kilowatt. Now we're talking 1.5, maybe 2 liters per minute per kilowatt. So that's at least a 50% increase in requirements just in the last couple of years. So it just shows how fast things are changing. And this has an impact on the physical topology as well. The higher densities change rack weight, floor loading, and the overall facility layout. So the integration decisions of how we put together the power, cooling, controls, they need to happen earlier, ideally in a factory, because the commissioning of these systems is where we typically see the scheduling risk come up. Now, the third hidden risk is the market landscapes. And what I have here on the screen is the cumulative AI chip power. And you can see that it's growing from about 2 gigawatts up to 13 gigawatts in just 2 years. The hyperscalers make up a big chunk of this, right? Their piece has gone up from about 1.5 to 8.5 gigawatts. And that makes sense because they're deploying at massive scale right now. But I think the other part of it is the more interesting piece. And that's the others, the neo clouds, the sovereign AI, the enterprise. Their portion has gone up from about 0.5 gigawatt to over 2. So they're showing a 4.5 to 5 times increase in that same time period. And so what that means is that multiple segments of the market are scaling massively all at the same time. But they're doing it with different architectures, different supply chains, and different levels of standardization. And all those differences create noise. And it's not because the demand isn't clear, because the demand is very clear. The demand is huge. But it's because the coordination does not scale at the same rate. And so the third and final hidden risk I'll cover is the disconnect of the standards. And this is one that is least discussed, I think, but it's also very technically interesting for the engineering community. And what you can see on this slide here is it's obviously not an exhaustive list of all the standards, but it shows the overlapping frameworks of facility standards, you have the management systems, you have the operational compliance requirements. And the issue isn't that the standards don't exist, because they obviously do. This is just a small piece of them. The issue is that they don't move at the same pace as the technology, and they don't align cleanly. They don't align cleanly across the standards. So let's go through a couple quick examples. The first is the shift towards 800 volt DC that we just talked about a few slides ago. That's obviously where the industry is headed, right? It's clearly what's going to be needed for next generation AI. But the certification framework for that is still maturing. You have both the UL and the IEC are working on it, but they're not fully harmonized yet. So what that means in practice is that companies are designing and deploying to systems while the standards are still being defined. So that creates engineering uncertainty for us. So you're making engineering decisions before you have a fully stable certification target. And the second example would be PUE, right? PUE is the most commonly used method to measure efficiency of a data center. And we know that it's widely used, but it's not consistently defined or really even enforced, right? We have the EN in Europe, we have the ASHRAE guidance, we have the hyperscalers' internal specs, and they all treat the calculation a little bit differently and report slightly differently. So a system that meets requirements in one region, if you moved it around, it might not meet another. And so when you're talking deployment at scale, that can turn into rework. And the third example that I'll touch on is liquid cooling, right? We just mentioned this a minute ago, that cooling rates themselves and the requirements are shifting quite quickly, right? The OCP guidance just 2 years ago was 1 liter per minute per kilowatt. It's increased by 50% now. And so that means in that short 2-year period, systems that were designed to meet the spec are now undersized, and certifications have been lagging that change. So the impact of all this is that redundant validation work, we have delayed qualification cycles, and products that pass one standard but maybe failing another. And most importantly, this can result in time lost during deployment. And when we're talking about these gigawatt deployments, even losing 1 week matters. So the bottom line of this is that standards are no longer just a compliance issue, they're a design variable. And the teams that engage early, especially reaching out to the standards bodies, are the ones that are going to avoid getting blocked later. So let me bring it back to the demand curve where we started. So again, just to summarize, 90 terawatt hours in 2025 to over 400 terawatt hours by 2030, 4 or 5 times increase for AI. Total data centers over 1,000 terawatt hours, and we expect the infrastructure spend to be over $1 trillion per year. But the challenge here is not whether or not the technology exists to accomplish this goal, because the technology does exist. The challenge is whether or not the industry can integrate these systems, validate them, certify them, and deploy them at the speed implied by this curve. And the point of the 3 different hidden risks that I talked about is not that they're independent, they're independent risks, because they're not. They compound on each other. You can have new topologies require new standards, and new standards can slow down deployment. You have market fragmentation increasing the variation, and variation increases our validation efforts. So all of this is happening while the industry is trying to do the 4 to 5 times increase for the AI infrastructure in the next 5 years. So the real constraint isn't the technology or the innovation, it's execution at scale. So to bring it all together, how do we get from where we are today to where do we want to be in 2030? I think there's a few practical shifts that we need to make as an industry. The first is we need to design systems, not components. The power, cooling, compute, and controls need to be co-designed as a single architecture, not integrated later on in the field. Second, we need to reduce the integration noise. We need to have fewer handoffs, fewer assumptions made between vendors, fewer surprises at commissioning, because the deployment delays typically come from the system integration effects, not from component failures. And the third is we need to engage the standards bodies earlier. We can't wait for the certification process at the end. We have to participate in shaping the standards, because the time the standards are finalized, you're likely already deploying those products. So to sum it all up, the challenge isn't just one of these things, it's all of these things together, right? And so if we're going to meet the requirements, to meet all these going forward, we have to design our systems as total products together before deploying them into the field. So that's the work that's in front of us as an industry. If you'd like to talk with us more about how Flex is going to address these challenges, please visit us at our booth, and I'd love to continue the conversation. Thank you.
感谢 Paul Diemer 先生精彩的分享。